Dr. T.P. Das, sir, please. Dr. T.P. Das, sir.
Hello, good evening.
Very good evening to you.
How is my
Special
audio?
I'm
Audio
doing
is
good. Thank you so much, Dr. T.P. Das, sir, for your very valuable presence today.
Thank you.
Dr. Vishwanath, sir, please. Dr. Vishwanath, sir, please.
Namaskar.
Sir, very good evening to you, Dr. Vishwanath.
Good evening.
Very good evening to you. On behalf of Explore the Space, I take pleasure in introducing Dr. Tirtha Pratim, our most honored chief guest for the day, who will be inaugurating this webinar, and Dr. Viswanathan, sir, a very eminent academician who has kindly agreed to give a special address today. We have friends joining from different parts of the country. We should be having Jaydeep, sir, very soon. We have about 95 to 100 registrations from 9 different colleges, the major one being Dr. M.G.R University. Thanks to Dr. Viswanathan, sir, for that. We should be starting in the next 5-10 minutes, and thank you so much. We will start with an inaugural by Dr. T.P. Das, that will be followed by a special address by Dr. Viswanathan, sir, and then the keynote address by Jaydeep, sir. We should start in the next 5-10 minutes. Dr. T.P. Das, is it audible?
Yeah, you're audible. And what about my audio?
Yes, you are very much audible.
Thank you.
Dr. Jaydeep, please. Dr. Jaydeep.
Yeah, okay.
Sir,
good evening.
very good morning to you, Dr. Jaydeep. It's a good morning for you. Good evening
Yep.
for all of us here, back here. Dr. Jaydeep, I take pleasure in introducing Dr. Tirtha Pratim and Dr. Viswanathan, two eminent men who are going to join the discussion today. So that's Dr. T.P. Das, the Director for Science Program in ISRO, who will be giving the inaugural. Dr. T.P. Das, that's Dr. Jaydeep, who has been a great inspiring friend for us in all our space education programs.
Nice to meet you.
Yeah, very happy to meet all of you. Wish you a very good day.
Thank you. Thank you. Dr. Viswanathan, sir, please.
Good morning.
Jaydeep, Jaydeep, we have Dr. Viswanathan here, an eminent educationist from this part of the world, who was formerly the Vice Chancellor of Anna University. Now he is the Rector for Dr. M.G.R University, who has been a very long association in the development of the space education and space industry. Thank you so much, Dr. Viswanathan, for joining today.
I was closely associated with Abdul Kalam for 30 years.
Oh, that's great.
Development project.
That's great. It's great to meet both of you.
Oh,
I just
very
want to
nice.
let you know, a couple of weeks ago, I had lunch with Dr. Somnath. He was visiting Kennedy Space Center. And I live very close by, just like 20 miles. So we met for lunch. I think he's the Vice Chancellor of some
Chanakya.
university.
Was that the Chanakya University?
Chanakya University, right. Yeah.
Okay.
This is this is a very interesting program. I mean, we are very glad to have a very senior person from ISRO and a very senior scientist from NASA. We consider all the participants as very fortunate to have both an official from ISRO and NASA speaking at this program. Dr. T.P. Das, would you like to comment something on that, please?
Yeah, it is indeed a good opportunity to inspire the students and letting them know about the prospects and how did everything evolved in our understanding about the universe and what are the things which are awaiting. So I look forward to this opportunity to speak to the students and wish you all the best for the success of this event.
Dr. Jaydeep, in one of your earlier presentations, you said that there is a launch every 28 hours. Every 20.
Yes, there is one at 6 o'clock my time. So that's a SpaceX Falcon 9 launch. And 4 hours later at 10 o'clock my time, there's a Atlas 5 launch from the Air Force. So we have two today. But yeah, there's at least 2 or 3 every week now.
Okay. Dr. Das, we had a very successful launch of the communication satellite that is to be added, that's adding to the prestige of the great work that ISRO is doing.
Yes. So we are very happy about this. And there is a long way ahead for to all the developments which are made available through the website of ISRO and also the press that is carrying the message about developments. So stay tuned.
The NISAR satellite has really put the cooperation between NASA and ISRO to the public view. Am I right, Dr. Das? Though the cooperation has always been there, I mean, it's more now to the public view. The cooperation between NASA and ISRO.
Yeah, definitely. It is one of the very important joint missions. So it has been a long legacy of preparation by the two space agencies and lots of dialogues, lots of technical activities, and finally it has come to reality. So I understand the scientific community who are working on the Earth system science will derive advantage out of this mission. So we also look forward to the good publications which are supposed to come out of this mission.
Okay. Thank you. We would start the actual program in the next few minutes to respect all those who have joined in time. We'll start sharp 6 o'clock. We just have a couple of minutes for that. Dr. Viswanathan, we heard about your successful trip to Uttar Pradesh. Something on that, please.
Yes, we are really glad to inform you that our satellite cancer testing was successful. Deployment, descending, opening of the parachute, everything was fine. We received the telemetry data and we are very happy. Also, rocket could not be launched because of the rain.
Weather.
So they postponed it. Another 3 months or 4 months it will take.
Congratulations to you.
Thank you. 2 batches, nearly 16 students we visited there. And they really, our students are interdisciplinary. All branches like computer science, 85% of the students are from computer science field.
Okay.
So they designed the rocket and everything they take care of it.
Okay.
It's really a very interesting movement. And I wish to congratulate the director, Tirtha Pratim. He's the best teacher I can say in the world because he made all our students. He made all our students work hard day and night and became experts in their field. And not suddenly, nearly 1 year, our students worked for this project. And I'm sure that India will have scientists from this group for establishing the Indian space station, as well as the astronauts landing on moon. Two missions, we have enough scientists with us.
Thank you, sir. That's very inspiring to listen to. Ladies and gentlemen, a warm welcome to all of you. Good morning to Jaydeep sir, who is now based at Florida. And good evening to friends in India. A special welcome to Dr. Tirtha Pratim and Dr. Viswanathan sir. Explore the Space is an ISRO registered space tutor. We have been conducting programs to promote space education, and we have had the special honor of working with Jaydeep sir for the last 6 years. Ever since we invited Dr. Jaydeep to address at a program at Bharatidasan University, Tiruchirappalli. That was way back in 2018. So thank you, Jaydeep sir, for your steady support to all our programs. Ladies and gentlemen, I take pleasure in introducing to you the chief guest for the program today, who has kindly consented to give the inaugural address. That is Dr. Tirtha Pratim. Dr. Tirtha Pratim is the Director of the Science Program Office at ISRO headquarters, who is the key person for planning and managing all scientific activities and space science missions of ISRO. With a distinguished career spanning more than 2 decades, Dr. Das has contributed to the Indian space program in several critical capacities. His work includes contributions to launch vehicle technology, high frequency phased array radar systems, sounding rocket experiments, scientific payload development for planetary exploration, and the formulation of space-borne experiments for interplanetary missions. Dr. Das also represents India on various international committees and working groups, strengthening global cooperation in space science and exploration. In his current role as Director of the Space Science Program Office, Dr. Das leads the development of India's space science strategy, fosters national scientific talent, supports academic collaborations, and advances space science education across the country. It is really our fortune that we have Dr. T.P. Das today with us to give his inaugural address. Over to you, Dr. T.P. Das, please.
Very good evening and very good morning to one and all. And my greetings to all the participants, especially the students and the teachers. As we know, this event is meant for the students, and I take this opportunity to congratulate the organizers for having taken this pain and passion to reach all of you. And I wish them all success in their future endeavors. So, as friends, as you are aware, astronomy is regarded as the oldest science, and it is born from necessity. It is born from the need of telling time, predicting the seasons, and also navigating by the early navigator sailors. And early astronomy, when we speak about it, it was dependent on the visible part of the electromagnetic spectrum, bare eyes of the human beings. And for obvious reasons, they were very much limited to the nearest objects like moon, the sun, and some of the planets, and the brightest stars which were visible from the earth. And the main tools were meticulous observation and strong sense of geometry. And you are aware how geometry flourished in different parts of this world and how much India also has contributed to the domain of geometry and trigonometry when it came to astronomy. That's how the mathematics and astronomy, observation astronomy, navigation, agriculture, everything got merged in a composite. Now it was in around 1609 when Galileo turned the first optical telescope towards the sky. And when it happened, the horizon of our rich disruptively got increased, and moon we could see different celestial bodies which were not that much visible when we used to see with bare eyes. And this telescope therefore expanded our known universe, and we could see the Jupiter, the moons around the Jupiter, the phases of different planets, and also millions of previously unseen stars. And that helped us appreciating that our sun, which is the prime mover of our solar system, is one of the stars, one of the billions of stars in the universe. And at the same time, when we grew in maturity and also in technology, we came to a state of appreciation that the ground-based astronomy had its own limitations. Like when you are dependent on telescopes which are on the ground, you are very much limited by the atmosphere, which absorbs most of the part of the electromagnetic spectrum, and also it introduces scattering of the photons, and eventually the atmosphere is opaque to different parts of the electromagnetic spectrum and also to the cosmic signals which are coming in the other parts of the energy range in the whole spectrum. And that's how the necessity of the space-based astronomy has emerged. And it was in 1950s, 1957, 58 timeframe when we were maturing, the humankind was maturing to step into the space age. And then we took this opportunity to do this observation from the space instead of limiting from the ground. And when it happened, we could go beyond the atmosphere and we started appreciating the advantages, and that was the birth of what we call to the space-based astronomy. And the importance was remarkable because the entire part of the electromagnetic spectrum was accessible, and the high energy, from the high energy gamma rays to the long wavelength radio waves, whatever you say, everything was accessible when we went to the space. And also very much remarkable was the infrared window, and which is very crucial because it could pierce even the different dust clouds, and which revealed even the birth of the different stars and different galactic cores which are otherwise hidden, we're not seeing using the visible part of the electromagnetic wavelength. And also it had a component of looking back to the history of the universe, because as we know that the universe is expanding, and which causes the distant this light from the distant objects to get redshifted, to get shifted to the longer part of the electromagnetic wavelength, to the infrared spectrum. And this could help us appreciating the dynamics of this universe, and people started taking into the realms of cosmology to extrapolate what might happen to the fate of the universe, taking into account the objects or the processes which we cannot sense, beyond which are beyond our observable limits. And that's how today we have come here to celebrate the success of the James Webb Space Telescope. And we have to also remember, before the launch of the James Webb Space Telescope, there have been precursor missions like Hubble Space Telescope, popularly known as the HST. It is a visible and near ultraviolet near infrared astronomy, space-based observatory. And that was the telescope, space-based telescope, which helped us showing the universe that full of and gave us the first deep field. And then also have to remember experimental scope of today whatever we are able to celebrate as the James Space Telescope. And when it comes to the James Webb Space Telescope, aspiration as the true successor of the Hubble Space Telescope, with lots of advancements and fundamental advancement in instrumentation. And it is addressing two fundamental questions about astronomy or astrophysics. How did the universe begin, and are we alone? Because it is also looking to components, which is very interesting, the exoplanets and the conditions of the atmosphere of the exoplanets. And human intellect never lags behind in understanding that there is still a possibility of somebody present like us in some of the exoplanets in exosolar systems, which might have some intelligence, not only limited to the formation of life, form of life, but they could be intelligent also. So that is one of the uh, components which the James Space Telescope opens up, apart from studying different processes using different parts of the electromagnetic spectrum, especially the infrared. And also, it has got its technological marvels like segmented primary emitters, quite a huge one, about 6 meter. And it is also a technological marvel because it is not easy to have a segmented primary emitter of this much dimension with all the structural properties requirements maintained and having it launched, keeping the thermal conditions and all other environmental conditions satisfied, which are very much required to met in a stringent fashion to meet the ambitious astronomical goals. The goals are also astronomical, and the requirements, technological requirements of this kind of a mission are also astronomical. And we also know the orbit is also a different kind. It is in the Sun at Lagrange point 2, and this is a stable and cold location, which is a conducive vantage point to see the sky without being baffled by the sunlight, which is coming from the sun. And if you see the scientific goals, they are quite fundamental and enormously interesting. The first light and reionization, as the astronomers mention it, which involves the detection of the fast stars and galaxies that were formed around 100 to 200 million years after the Big Bang, which caused the end of the so-called cosmic dark ages. So when we say when the stars and galaxies which form the realm of astronomy, those were not there. What was there after the Big Bang? And that's how we speak in the realms of cosmology. And this transition also is being studied by our James Webb Space Telescope. Also studied the realm of the galaxy evolution, star and planet formation, physics of star and planet formation, and as I have mentioned, the physics of the exoplanets, and also addressing the aspects of the habitability in different exoplanets. And at this juncture, let me take this opportunity to speak about you, the Indian context about our space-based observation in AstroSat, which have been in the sky from 2015, and which is India's first multi-wavelength astronomical observatory, which has already in its credit several discovery class of findings. I am not going to those regimes of discussions. Time will not permit me, but it is quite a big list. The achievements of the AstroSat, and very recently we have flown the ExpoSat mission to study the bright X-ray sources in terms of its variation of intensity, spectroscopy studies, and also the polarization coming from the different bright astronomical X-ray sources. And all these are India's preparations for the self-reliance, which we called the Atmanirbhar Bharat, to take it forward, not really limited to the electromagnetic wave-based exploration of the space, because we have started speaking about the multi-messenger astronomy, whereas not only the photons, we are also speaking about the astronomy with the help of the gravitational waves, neutrinos, and also the cosmic rays to get a holistic view. And the work has started, as you know. LIGO India has also already got nod from the government of India, which is definitely the ground-based observation. But there also have been discussions happening about space-based gravitational wave observation, although it has not come to a level of maturity, but the discussions are still happening. Let me conclude my short speech with a very special message to the students about the interdisciplinary role of different subjects. And this is very important. The space-based astronomy is no longer limited to the physicists or the students of physics. Whatever branch you're studying is necessary. No subject is left out in space science and technology. To the physics students, if I even speak in terms of the James Webb Space Telescope for astronomy, developing and refining the theoretical models, suppose, is in the realm of the physics students. And you can always speak about the astrophysics, which is behind the astronomical observations. Physics students will have a lot of opportunity to explain the results which are going to come from the James Webb Space Telescope. Coming to the mathematics student, you also have a lot of things to offer, like you can contribute to the algorithm design, creating algorithms for, say, deconvolution of different complex problems when the light comes to your deep space network. A lot of phenomena happen in between. Gravitational fields bend your light. Photons, the electromagnetic waves undergo a lot of changes because of different magnetic fields and processes in the medium. So how to deconvolute all the processes, get the actual physics and process what is happening in the astronomical sources. If mathematics students don't come to this field, who else will do? So mathematics students were most welcome. Same thing I will tell about the chemistry students, because the emerging branch is astrochemistry, where the work is to analyze the molecular signatures in the exoplanet atmospheres and interstellar clouds, which will give you a bigger perspective of not only astrobiology but also the geochemical conditions in the universe, which have been responsible for evolution of different facets of this universe today, whatever we see in its form. And also biology students, if somebody is listening, you are also not left out, because defining the chemical and atmospheric markers, which we call the biosignatures, is your job. That would indicate the life on the other planets, and which may guide the James Webb Space Telescope observation. And engineers, you are very much necessary, whether you are from the mechanical, electrical, or aerospace background, for designing next generation space instruments, cryogenic coolers, the one which is being used by our missions like James Webb, and especially the ones which should avoid the thermal noise, advanced version of those. Also for using advanced technologies like quantum computing, where you are making use of very huge computational capability by making superposition of lot of wave functions. That also needs a lot of thermal engineering and other domains of engineering. So nobody is left out. And before I conclude, let me tell you the emerging branch today, irrespective of all these domains, domain knowledge is very important, no doubt about that. You study physics, chemistry, mathematics, biology, whatever. Then it comes the realm of artificial intelligence and machine learning. Let me tell you about a few cases, very recent cases, which have been very much motivating. Are you aware that an 18-year-old student recently has developed an artificial intelligence algorithm to analyze the data from our Neowise telescope of NASA, which has been retired? He has seen the historical data, and he has identified using his artificial intelligence techniques about 1.5 million potential new objects. And also, he is one example, but artificial intelligence, machine learning techniques, which are also now imbibing deep learning, this is making possible to go to very deep sense of pattern recognition and look at the data, even the historical data, to find out which we could not have found so far using our conventional techniques. And also different other processes, like not only about astronomy, whatever we call to the planetary defense. Today we know that your comet Atlas is coming, and it has shown some peculiar properties. People are telling so many things about this extraterrestrial object, whether it is natural or artificial. Artificial intelligence might have some say to speak on its interpretation, on its astro dynamics. And also improved image analysis, and also finding new objects in the solar system and beyond. The list goes on like this. In this, I take this opportunity to call Space Telescope is not an and it's a tool that would generate more questions than answers. That is true for not only James Webb Telescope but any mission. Our mission is not only but new questions which you might whatever will come in this and the next generation who are attending from this room virtually, and engage with this data, because the data are open as a policy from different space agencies. Go through the data, do projects with this data, and you're the generation that will apply all these messengers and missions to understand our universe and also to generate a lot of capabilities technologies. Some of the technologies will have definitely some spin-offs. Yes, sir. I have done.
Thank you so much, Dr. Thank you so much, Dr. T.P. Das, for your very inspiring inaugural address. Particularly when you said that space industry and space technology is driven by multidisciplinary approach. Your mention of physics, chemistry, and mathematics was really inspiring, and your special mention of AI and ML adds to the growing interest in that subject. Thank you so much, Dr. T.P. Das, for your presence today and for inaugurating this highly interesting webinar. Ladies and gentlemen, now I take pleasure in welcoming Dr. Viswanathan sir for his special address. Dr. Viswanathan sir, as I mentioned, is a very eminent academician, currently Rector, Research and Development at Dr. M.G.R. Educational and Research Institute. Formerly, Dr. Viswanathan served as the Vice Chancellor of the famous Anna University. Dr. Viswanathan has had the unique distinction of having done his PhD research supported the Trishul missile project under the guidance of Dr. APJ Abdul Kalam. This was way back in 1984, which resulted in breakthrough superplastic forming technology for titanium alloys, which are used in aircraft, rockets, and missiles. Dr. Viswanathan, it's a pleasure having you here, sir. Over to you for your special address, please.
Thank you, sir. Good evening to everyone here in India, and a good morning to our distinguished guests joining from the United States, including Dr. Jaydeep Mukherjee from the NASA, Florida Space Grant Consortium. It is a genuine honor to address this gathering of curious minds, experienced faculty, and our all-important future leaders, the students. Today, we are here to discuss instrument that is fundamentally changing not just what we know about the cosmos, but we can know. I am speaking, of course, about the James Webb Space Telescope. Before going into the technology activity, James Webb Space Telescope, I would like to congratulate Dr. Venkatagiri, CEO of Explore the Space Organization. He's doing extensive promotion of space education among the young minds. I really fascinated by his service to the humankind in India. And also, I'm really grateful to Dr. Jaydeep Mukherjee and Dr. Tirtha Pratim who participated in this presentation. All my students will be highly benefited. About a word about M.G.R. University. 5 years before we initiated the activities on space education and space technology, we have signed an MOU with the Indian Technology Congress Association, Bangalore, after joining with the Prime Minister's mission of 75 satellites mission. And this developing CubeSat for the benefit of Indian fishermen is ongoing. It will be soon launched by ISRO in the near future. And this Space Center in M.G.R. University, we have organized 3 national seminars. Nearly 900 students from various colleges in Tamil Nadu participated, and nearly 100 school students. We gave an awareness for school students in conducting competitions in the space field. With this, I would like to say a few words. I am not a space scientist, but I am a teacher who guide and motivate the students. Recently, our students participated in the competitions conducted by InSpace at Gorakhpur, and the satellite was successfully launched, deployed, and then descending, delimited data all received. So rocket will be launched soon. And that day, because of rain, the rocket could not be launched. Now, This is not merely another telescope, it is an engineering marvel, a time machine, and a profound testament to human ingenuity and persistence. This telescope, I am not much knowledgeable, but we are expecting our Dr. Jaydeep Mukherjee will be able to give you a very extensive explanation about the telescope. But a few points I would like to mention here. Its 6.5-meter primary mirror, a stunning honeycomb of 18 gold-coated beryllium segments, is the largest ever launched into space. That gold creating is not for decoration. It is specifically optimized for reflecting infrared light, which is invisible to our eyes. Its 5-layer tennis court-sized sun shield is an equal marvel, designed to protect its sensitive instruments from the light of the sun, earth, and moon. This shield source allows the telescope to operate at a frigid minus 233 degrees Celsius. This extreme cold is essential because to see the faint, warm glow of distant galaxy, the telescope itself must be impeccably cold, ensuring its own heat doesn't blind its own vision. Why this extreme design? To see the universe in infrared light. This capability allows Webb to do what the legendary Hubble Space Telescope never could. It peers through the vast cold curtains of cosmic dust that is opaque to visible light, to watch the very birth stars and planets hidden within. More profoundly, it looks back in time. As the universe has expanded, this ancient light has been stretched or redshifted into the infrared spectrum. Webb was built to catch these faint, stretched whispers from the dawn of creation. And the results, even in the first few years, are already revolutionary. In September of this year, 2025, it gave us the first ever direct chemical analysis of potential moon-forming disk around an exoplanet. We are no longer just finding planets. We are now capable of studying the very nurseries where the moons are born, analyzing the raw materials, the rock, ice, and organics that are coming together to build worlds. But the pace of discovery is accelerating. Just days ago, at the end of October, astronomers released the first ever 3D atmospheric map of an exoplanet. Using Webb, they mapped the ultra-hot Jupiter, WASP-18b, creating what is essentially a detailed weather map of an alien world. They found a scorching hot side where temperatures are so extreme, they literally tear water molecules apart. This is not just cataloging planets. This is the dawn of a new frontier, comparative climatology, where we can study alien weather to better understand the forces that shape all atmospheres, including our own. I would like to touch upon the importance of space education. As our Dr. Venkatagiri is carrying it out, the young minds of this country is very much interested and explore the space more. Hence, since the dawn of civilization, we have looked upon at the night sky with wonder. From the ancient astronomers who studied the stars using simple instruments to today's scientists who explore distant galaxies with advanced telescopes and spacecraft, humanity's journey into space has been one of relentless curiosity, courage, and discovery. But today, space is not a distant dream. It is part of our daily life. When you check the weather forecast before leaving home, when farmers receive information about rainfall or crop health, when rescue teams monitor floods or cyclones, all these depend on satellites orbiting high above us. Space technology silently supports communication, navigation, education, environmental protection, and national security. This is why space technology education is not just about launching rockets or visiting Mars. It is about building knowledge, skills, and vision for a better world. Space education brings together multiple disciplines: physics, mathematics, computer science, electronics, materials engineering, and environmental studies. It encourages critical thinking, creativity, and problem solving, skills that are essential for the 21st century workforce. When students learn about space missions, orbits, and satellites, they are not only studying science, they are learning teamwork, perseverance, and innovation. Let us take inspiration from India's remarkable journey in space. When ISRO was established in 1969, the world did not expect a developing nation to achieve much in this high-tech domain. But India proved otherwise, from launching small satellites to reaching the moon and Mars, and now exploring the sun with Aditya L1. India has shown what determination, innovation, and education can achieve. Remember the excitement of Chandrayaan 3 landing near the moon's south pole? It was not just a scientific trip, it was a moment of national pride. It showed millions of students that dreams powered by education and hard work can truly take us beyond the sky. Today, India's space technology contributes to climate monitoring, disaster management, natural resource mapping, and digital connectivity. And all these achievements begin in classrooms, where young minds are inspired to ask questions like why not and what if. That is why schools, colleges, and universities must integrate space education into their curricula. Hands-on experiments, model rocketry, astronomy clubs, and collaborations with space research institutions can ignite their lifelong passion for science and exploration. We must also recognize the role of teachers and mentors who guide students in this journey. When educators connect space science to real-world challenges, from climate change to sustainability, they prepare students not just for careers, but for global citizens. Space education also promotes international cooperation. The exploration of space belongs to no single nation. It is a shared human endeavor, one what unites scientists, engineers, and dreamers from every corner of the world. By encouraging our youth to think beyond borders, we nurture peace, progress, and shared discovery. Space technology education is an investment in the future, a future of innovation, discovery, and hope. It helps us explore the universe, understand our planet, and create technologies that improve life on Earth. But above all, it teaches us to dream, to look upward, think forward, and believe that the impossible can become possible. So, let us inspire every young mind to reach for the stars, not just to explore space, but to create a brighter, smarter, and more sustainable world here on Earth. Why do we invest in space? Why do we, as an educational and research institute, campaign this cause? The answer extends far beyond astronomy. First one, space is the ultimate driver for STEM, science, technology, engineering, and mathematics. Do not exist in a vacuum. They need a purpose. They need a challenge. Space provides the most compelling, high stakes, real world application for every one of these fields. Want to teach physics? Don't just show them an equation for gravity. Show them how we use a precise gravitational slingshot to accelerate a spacecraft toward Jupiter using the planet's own orbital energy. That is orbital mechanics in action. Want to teach engineering? Don't just talk about material science. Talk about the challenge of designing a sun shield that must be light enough to launch, strong enough to survive a rocket's vibration, and smart enough to fold 12 times and then fold flawlessly, a million miles from the nearest human. That one task involves material science, robotics, thermodynamics, and complex systems modeling. Studies from leading educational organizations consistently show that the student engagement with the space-related curricula significantly increases interest and proficiency in STEM subjects. The Apollo effect inspired a generation to become scientists and engineers. We are now seeing the Webb effect and the ISRO effect. Do the same for our students today. We are not just training astronomers. We are inspiring the next generation of engineers, data scientists, material scientists, and most importantly, creative problem solvers. The challenges of space demand excellence, and in doing so, create it. The second one is the space education is a direct investment in our future economy and workforce. The space economy is not a futuristic fantasy. It is a multi-billion-dollar global industry, and it's growing rapidly. This economy is not just about astronauts and rockets. It is about the vast downstream applications, the telecommunications that connect our world, the data analytics that interpret each observation signals, the GPS in our phones, and the satellite imaging that monitor climate change, predicts cyclones, and improves agricultural crop yields. By fostering space education, we are giving our students a critical competitive advantage. We are preparing them for the high value, high tech jobs of the 21st century. An institution that ignores space is failing to prepare its students for the future. We at Dr. M.G.R. Educational Research Institute do not intend to make that mistake. In fact, we have decided to start B.Tech minor degree in space technology, comprising for all students, all branches of studies. Not only engineering, but also humanities and science. We are introducing the minor degree this year. The digital imaging sensor in your mobile phone camera, that is a direct descendant of the CMOS technology NASA developed to create small, low-power, high-resolution cameras for its spacecrafts. The third point which I want to say is the most crucial one. Space education fosters a perspective that is desperately needed in our world today, a global perspective. Look at the poster for this very webinar. It has two dates, two time zones, one for India, one for the USA. Our keynote speakers are from ISRO and NASA. This is not a coincidence. This is the very nature of modern space exploration. From the vantage point of space, the divisions on Earth disappear. Astronomers call this the overview effect, the profound cognitive shift that occurs when they see our planet as a single, fragile, blue marble floating on the dark. There are no political borders visible from the moon. Space education is an attempt to give that perspective to everyone. The International Space Station, orbiting our planet 16 times a day, is arguably the most complex and successful example of peaceful international collaboration in human history. At this time, I would like to mention that India's mission by 2035, India wants to establish the Indian Space Station. And 2040, Indian astronauts will land on moon. These are all our mission. We have a great responsibility in bringing scientists for these requirements. And I want to tell to our young student friends that ISRO has achieved a great extent by launching 104 satellites in one PSLV rocket. It's a great mission, and we have launched Chandrayaan in 2023, and we have the missions like Mangalyaan and Aditya L1. All these things are going on very well. This week, they launched a 4,410 kg great mass payload of their rocket. All these things are very good. And my students, friends, by working in this field, don't expect that you will automatically get into ISRO for your career. You have to go through selection process. And there are about 300 startups have come in India. You have tremendous opportunities if you take interest and work in this field. I wish you all the best. I conclude thanking the organizers for giving me an opportunity in this program. Thank you.
Thank you. Thank you very much, Dr. Viswanathan, sir. Particularly your emphasis on the importance of space education and the growing importance of a global perspective. Those are very encouraging and very, very important. That that only gives us the depth of the subject that we are handling. Thank you so much. Your presence and your address is an inspiration, and we sincerely wish to travel along with you for the long years to come. Thank you again, Dr. Viswanathan, sir. Ladies and gentlemen, now I take pleasure in introducing to you the keynote speaker of the day, the great scientist from NASA, Dr. Jaydeep, sir. Dr. Jaydeep Mukherjee serves as the director of the NASA Florida Space Grant Consortium, Florida. Under his leadership, the consortium plays a key role in advancing NASA's mission by fostering education, research, and workforce development in space science, aerospace engineering, and STEM disciplines across the state of Florida. Dr. Mukherjee oversees strategic partnerships with universities, industry, government agencies, and NASA centers, offering research grant fellowships, scholarships, and hands on aerospace training opportunities for students and researchers. Dr. Mukherjee is widely recognized for his dedication to advancing space science education and nurturing talent that contributes to the growth of the global space ecosystem. Friends, in the last 4 years, this is the sixth address that we have had the pleasure and opportunity of hosting Dr. Jaydeep sir, especially on James Webb Space Telescope. That's an honor for us. And thank you so much, Dr. Jaydeep. Over to you, Jaydeep, please.
Thank you for inviting me to address the students. Great introduction by Dr. Das and Dr. Viswanathan. I relate very closely with Dr. Viswanathan because I'm more of an educator now than a scientist. And I've been working with students and faculty for 25 years. And I just totally agree with everything that Dr. Viswanathan said. So let me share my screen first and then I'll start talking, and if I can figure out a way. I'm doing this for years, but yet, there you go. Do you see my screen?
Yes, sir. Yes, sir. I'm able to. Yeah.
Okay. Okay. So I know most of the students are engineering students. So I think what I'll do is I'm going to have two parts to this talk. The first part is about the telescope itself, why we chose the telescope, how it was built, because it's an engineering marvel. So my background is in astronomy and astrophysics, but I've been working with engineers and students, and I just hats off to the engineers, because without them, we couldn't do any of the science that the rest of the world is doing. So I really want to talk a bit about the engineering. And then the second part is talk about these amazing discoveries that the James Webb Telescope has done. It has made us rethink how galaxies form, how black holes form, and even the formation of the universe. We don't have any answers as yet. We have more questions than we can answer, but that's the beauty of science. That's what makes us drive is to answer these questions. So before I start, I'm going to show you a 2.5 minute video, it's like a teaser trailer about the James Webb Telescope, so that you have an idea of what this talk is going to prevent. So give me a second. And so this is a NASA 2 minute video clip on the telescope itself. So that gives you an idea of what I'm going to talk about. But there are a lot of questions before that. Why choose to build the James Webb Telescope? It's very, very expensive. Well, it all comes from surveying scientists and astronomers. And here in the US, every 10 years, we have what is called as a decadal survey, where we ask the top scientists and engineers to come together to decide what NASA or the National Science Foundation should fund in the next 10 years. So they came up, and I think Dr. Das did touch on this. They come up with 3 questions that we need to answer. Where did we come from? How did we get there? Are we alone? So you want to answer these 3 questions. And I think every one of you, I know when I was a kid and growing up, I used to go crazy wondering some of these questions. Are we alone in the universe? If we were not there, what is a universe? So the reason why we are humans and why we are different than apes or other animals is because of our quest for knowledge. Okay? Apart from the fact that the space program, as Dr. Viswanathan has repeatedly mentioned, we have transferred the technology to the private sector, to the public. A lot of things that we see, from GPS to Velcro to pacemaker, all came as a result of space technology. But beyond that, what makes us different than any other species on the earth is a quest for knowledge. Without that, we are not a good civilization. So that's why these 3 questions are very, very important. So basically, what we're doing is an astronomical search for our origins. We start with what's called the Big Bang. That's the so-called formation of the universe. Then the first galaxies form. Then the galaxies evolve. Okay, and from the galaxies actually made up of stars. The stars have planets, and planets will have life. So far, we only know of one planet which has life, and that's the Earth. But I think in your lifetime, for some of the students, we will detect microbiological life form in one of the moons of our in the solar system, whether it's Europa around Jupiter or Enceladus around Saturn. We will find. Technology is getting better and better, but the main reason for this telescope launch is the search for our origins and answering all these questions. But as I said, it's engineering which actually leads to the success of the science. But it's the other way around. The science is what is driving the design. Why do we need a 6-meter telescope? Why does it have to be in space? Why has it to be infrared? It's because of some science questions we want to answer. So if we look at it, we want to see faint stars and galaxies. The only way we can do that is if we have a very big telescope, a big mirror. Larger the mirror, larger the light gathering power, the fainter object we can see. We also want it to be in space because we don't want the atmosphere to block most of the radiation. So we want it to be deployable and want to be lightweight because you have to launch it with a rocket. And in any launch with a rocket, the main problem is the cost, and the main cost is the fuel. So if you have anything heavy on a rocket, that'll ask us to put more fuel, that'll make it more expensive, and it goes on and on. So you have to make it very lightweight. And I'll talk to you a bit about all this soon. If you want to see the earliest stars and galaxies, and if you want to peer through the clouds and the dust around stars, we need to look at the infrared. And I'm going to talk about infrared in a couple of slides, just to give you a background. And I apologize if all of you know about this, but I'm not very sure about what kind of students are listening to the talk. So I just have a few slides on infrared and Dopplership. But if you want to do that, we need to be seeing the infrared, and we need something. We need very cold temperatures because without that, we cannot detect infrared radiation. And of course, Dr. Viswanathan talked about having a sun shield to block the heat and the radiation from the sun and the moon. So those are some of the requirements. And then if you want to look at exoplanets, we need to have spectroscopic capabilities, which means you break up the light into different features, and we can study the spectra and learn more about the atmosphere. Just to give you an idea, exoplanets, in the last 5 to 10 years, we have discovered so many planets around other stars. Think about it. Our galaxy has about 200 billion stars, okay, at least. Our star has about 8 planets. Forget the other comets and dwarf planets. Even if we take an average of 1 planet a star, there are at least 200 billion planets in our galaxy itself. There are more than 200 billion galaxies in our observable universe. Imagine the number of planets that exist in a universe. Of course, hopefully, some of them will have life. We have no evidence of it. Unless we have evidence, we cannot say. But that's what we want to find out. So exoplanet exploration is very, very important. So the 3 key facts to get all the answers: we need a space telescope, we need an infrared telescope, and we need a telescope with a large aperture, a big mirror, because without that, we cannot see faint objects. So the next 3-4 slides is just to give you a background on the electromagnetic radiation, Doppler, Rector, and redshift, just to give you some fundamentals as I talk about observations later on. So let's talk about what we mean by redshift and infrared radiation very, very briefly. All of you know about the electromagnetic radiation, right? You have everything from radio waves all the way to X-rays. It's all around us. Our eyes are a detector for visible. So we can see light from the stars, from the sun, and so on. We do not really detect UV and the others, but we have detectors to detect them. What is important to see is that the temperatures, which causes all these different kinds of radiation. So if it is very hot temperature, you'll have mostly X-rays and ultraviolet. If it is low temperature, we have radio, microwave, infrared. Now, a lot of this dust on planets are so cold that it is mostly emitting infrared. I'll talk to you a bit about redshift, but the light that we are seeing coming from the farthest galaxies has been stretched from visible to infrared. And that's why we are more concerned with the infrared portion to answer these questions. And I'll tell you more about this soon. Now, of course, you guys are all engineering and science students, so you know this, but I just want to show you just an example of Doppler effect in terms of sound waves. So you have a source which is emitting sound waves. Now, as the source is moving towards the observer, you see how the waves are getting squished, okay? And as it goes away from an observer, the waves are actually stretching. So this is for the sound. And you have heard this when you are in a rail station and you approach, you hear a train approaching you and going away, you hear this. Hold on 1 second. Sorry, hold on. This. So there you go. A train is approaching you. There's a change in the pitch. And then it goes away from you. Pitch decreases. And that's what we call Doppler effect. And that is for sound. Same thing for light. There you go. If we look at light coming from a star, if the source of the light is going away from the observer, the light is stretched. The waves are stretched. And we call it redshift because red has a longer wavelength than blue. If the source is coming towards you, the waves are squished and it's more towards the blue part of the spectrum, and we call it blue shift. And from this Doppler shift in spectra that we get from other objects, we can find the distance to stars, what kind of elements are in the atmosphere, and so on. But when we talk about objects far away from us, we need to talk about what is called the cosmological redshift. I talked about the redshift, which is due to the movement of a source with respect to a target, right? But what is happening is we know that the Earth, our universe is expanding. And it's expanding rapidly, actually. So when the universe expands, if you have, say, a light, like blue light, and as the universe expands, then the blue light is stretched more towards the red part of the spectrum. So what is happening is as the universe expands, it's not that galaxies are expanding, it's not that we are expanding, it's the space between the galaxies which is being stretched, and that stretches the radiation. So light which left galaxies billions of years ago in the visible, for us to detect it, we have to look at the infrared, which has been stretched so much. And that's why it's called the cosmological redshift. Here's the, as I was saying, you have all this radiation, gamma rays to radio waves. If it's emitting in the visible, as the universe expands, it actually goes more towards the infrared. So we need to have an infrared detector or a telescope to detect the light or the radiation from galaxies which were formed a few billion years from the formation of the universe. Here's an example of the sun, which is the visible light which we see. Our eyes is a detector for light. And here's some example of infrared images. Okay, so in the case of a human being holding a matchstick, this is the brightest part because that's the hottest. Our eyes are actually very cold, so it's more bluer in color. That's the color combination. White is hottest, blue is cooler. Same thing, we look at the cat, we look at footprints. These are infrared images. Here's some more examples of visible images and then infrared images. But we learn a lot from these different types of radiation. So, what is the James Webb Telescope? I'll try to give you a very quick background. So, what is the James Webb Telescope? It's an infrared telescope, okay, trying to detect infrared radiation. It's very large, 6.5 meters. It's a successor to the Hubble Space Telescope, which is orbiting the Earth. It's an international collaboration between Europe, USA, and Canada. The senior project scientist is Dr. John Mather, who is a Nobel laureate. Total cost, as you see, it's very, very expensive, more than $8 billion. And it was launched in 2021 from French Guiana. And I'll tell you why it was launched from there. These are some of the international partners. The Canadian Space Agency gave 2 science instruments. NASA was a mission and observatory. And the European Space Agencies gave 2 science instruments, the rocket and the launch. So it was really an international program. The main thing about this telescope is the mirror, right? It has to be a large mirror. Think about this. Look at, if you take say a 5-watt bulb on the small bulbs, if you take that and you keep it on the moon and you try to observe the light from the Earth, the James Webb telescopes are looking at objects where the light is about 1/20th of that of a 5-watt bulb on the moon, as seen from the Earth. Imagine how faint that light is. So we need to have a large telescope so it can gather the light. The larger the telescope, the more light it can gather, the fainter the object we can see. So example, say if you take a bucket and it's raining, if you have a small bucket, you only collect a small amount of rain. But if you have a wider bucket, then it'll collect more rain. Same thing in the case of mirrors, we need to have a large mirror so it can collect a lot of these photons of light. And here's the mirror. So we cannot have just one huge mirror, because if you want one huge mirror which is 6 meters across, it will be so heavy, it'll sag in the middle. Also, if it is a very big mirror, we cannot place it in the rocket. Because again, as I said, the bigger the rocket, more fuel, more expensive. So we need to figure out a way how we can fold the mirror. So the way to do this is to have different segments. So the James Webb Telescope has about 16 segmented mirrors, okay, joined together. Now, why are they hexagonal in shape, each of the segments? Think about it. If each of the segment, if there were circles, then the circles don't fit each other very well. There'll be gaps if you want to make one full mirror out of that. If you take square mirrors, again, not very good because they don't focus the light to the central part of the detectors. If you have oval mirrors, again, the images will be distorted. The best way to have a segmented structure is this hexagonal, because now you don't see any gap as you fit the mirrors together. And look how large the primary telescope mirror is compared to the Hubble telescope mirror right over here. The main thing also is the weight. We have figured out a way to make a bigger telescope using materials which are very light. And so here we have the James Webb Telescope mirror, even though it's quite larger than the Hubble, is about 62% lighter than Hubble's mirror. That's the advance in technology. But the main thing is the light gathering power. It's not the diameter, it's the light gathering power. So with the James Webb Telescope, look at the light gathering power. This is just the wavelength, different types of radiation that you can observe. And this is the light gathering power. Look at the James Webb Telescope. A wide range of radiation, mostly in the infrared, but a lot of light gathering power compared to the Hubble Space Telescope, which is visible and partly infrared, or the Spitzer, which is a totally infrared spacecraft, but is very, very small. So you see, just comparing the three space telescopes, James Webb Telescope is amazing. So as I said, there are 18 segments. I was wrong, not 16. There were 18 segments, each 1.5 meters across. It's made up of beryllium, which actually is stiffer than steel. It's not as strong as steel, but it's stiffer than steel. And it is not deformed at cold temperatures, because that's what the temperatures are going to be very, very cold. And at that temperature, beryllium does not deform. So we use that. It's lightweighted, but it's not really reflective. Beryllium is not reflective at all, not very good reflection. So you need to coat it with gold. 0.1 micron. 1 micron is 0.001 millimeters. So we're talking about coating with a thin layer of gold. And as Dr. Viswanathan said, it's gold because gold can reflect infrared radiation very well. And just to give you the amount of gold that we needed, if you take the weight of a golf ball, about 48 grams is all the gold we needed to coat the mirrors. It's not a lot. Now, the other problem is that you have these 18 different segments. If they're not aligned very well, you're going to get out of focus images. So we have small motors behind each of these mirrors. They're called actuators, and they're computer controlled. And I'll show you an animation soon how they can move these segments by small amounts so that eventually we get one focus of an image. And I'll show you an animation soon. The other important part which Dr. Viswanathan and Dr. Das mentioned is the sun shield. We need to protect the instruments from the heat and the radiation from other objects of the sun and the moon and so on. If we do not protect it, the instruments will not work because they have to be at very cold temperatures. So these sun shields, it's actually the size of a tennis court, and they're made up of 5 layers. You don't want just one layer, because one layer you can conduct heat through the layer. But you have 5 different layers with gaps in between. We can re-radiate the heat away. So the sun shield is actually the size of a tennis court, but it's very reflective and made up of 5 layers. And is actually coated, it's made up of a material called captain, which was invented by DuPont in the 60s. We're using that, but we are coating it with aluminum because it's very reflective. It can reflect sunlight and the heat away. And then we have these 5 different layers to re-radiate the heat away. It shows how large the sun shield is compared to humans. So here you go, the 2 sides of the Webb telescope. You have this sun shield. On the hot side facing the sun, it can be about 85 degrees Celsius. that is too hot for all the instruments. The instruments are behind the sun shield out here. It has to be very cold. But the sun shield, as it blocks most of the heat, on the cold side, it's about minus 230 degrees Celsius. See, imagine going from 85 degrees to minus 200 degrees through this heat shield. It's an amazing feat of engineering. And without that, the telescope wouldn't survive. So what it does is you have the sunlight and there's 5 layers. Now, heat might go through the first layer, but then each level blocks some and deflect the rest harmlessly out the sides. And by the time we come to the 5th layer, the temperatures are enough so that the instruments can work very well. This again is an example. I don't want to go into details of this. We have a primary mirror, we have a secondary mirror. What is important is for the engineers is the spacecraft bus. The spacecraft bus is actually operating the whole spacecraft, James Webb Telescope. And that's where it is located. We have star trackers so that we can track the star to find out the location with respect to the stars. And again, these are for the engineers. If you build any small, even in a CubeSat, a 10 centimeter by 10 by 10, we need to have these different subsystems. So electrical power system would be like, say, converting the sunlight to power some of the instruments. The attitude control is the orientation of the spacecraft, pointing in the right direction. Communication subsystem is communicating with the different parts of the system. Command and data handling is like the brain of the whole bus. Propulsion system is the fuel and small rockets we need to actually adjust the orbit of the telescope. The thermal control subsystem is basically trying to keep low temperatures. All of them are important. All of them need to work. And the best thing is, when engineers work, they work on different subsystems. So if you're a group of students trying to build a CubeSat, they're going to break it up into these 6 groups, and each group will work on these different subsystems. And here's a mock-up of the spacecraft bus on the right. As I said, there are 4 instruments, 2 by the US and 2 by the European Space Agency. One of them was provided by the University of Arizona. So students are playing a big role in this. And 2 of them from the European Space Agency. And this is where the instruments are located, the 4 instruments. Just to give you an idea, what's inside the instruments. So you have cameras that can take pictures. You have spectrographs that break light into colors for analysis. And then something called coronagraphs, which can block the starlight so you can see the planets around or the dust around the star. So these different instruments have different, for example, the NIR spec, it's mostly spectrographic, just a spectroscopic instrument. The NIRCam, near infrared camera, can take pictures, can do spectroscopy, and also be a coronagraph. The same thing with the other 2. So you have 3 different types of instruments inside the instruments. Quickly about the launch, as I said, it was launched in French Guiana, which is very close to the equator. Why launch from the equator? Why not launch in the north, above, or below? The reason is that we want to conserve fuel, right? So if we take any point of the equator, any point of the equator is going to travel faster than any point above or below the equator. Okay, so because any point of the equator is traveling fastest, we want to launch from the equator, because as you launch, it already has the speed of the Earth's rotation. And you want to launch east, because you don't want to go against the rotation of the Earth. So you want to launch east and get the maximum speed of the Earth. You launch more near the equator and more near a place where when the rocket launches, it goes over an ocean. You do not want to launch a rocket over land, because if something happens to the rocket, it explodes, it'll fall on the land and on the population. So most of the launch pads, whether it's in India or elsewhere, except for Russia, where it's the middle of a desert. It's actually on a coast towards the east and launching towards the east. So that's why they tried to launch French Guiana. The European Space Agency has a launch pad in French Guiana. And again, as I said, the Webb telescope is folded because without folding the mirror, you cannot fit it into the rocket. And there's a fairing which goes over the telescope to protect the telescope during the launch. And this shows you the configuration. As you can see, you have the telescope right over here. But then you have other parts of the rocket, right? You need fuel, you need the rocket boosters, the shielding and everything. So here's an example of the whole Ariane 5 rocket with the James Webb Telescope as the payload, and then the rocket engines and the rocket boosters and the fuel and so on. It's a very short animation because, again, I think it's so impressive. Remember, everything has to go right. There are so many moving parts. And if one thing fails, the whole telescope is a failure. And there is no way we can go and repair the telescope. So just to give you a very quick idea of so now you have the solar panels which are protruding out to gather power. You have the radar to communicate with the Earth, and now you have the sun shields, which are from both sides, which are being deployed. You only see one layer now, but then you'll see 5 different layers. And you also see the mirror, which is folded right now. But here's the mirror segment. So here's the sun shield exposing the reflective layer. Again, these are all done automatically, all pre-programmed. If one of them fails, the whole thing is gone. $6.5 billion down the drain. So again, here you go. Here you see the sun shield. And now you can see the different layers, which is very, very important than having just 5 layers. And now you see the primary mirror. It was folded. Now you unfold it and it becomes this huge, big mirror. So I told you that, the light, you have different segments. They have to be very, very much aligned. So this animation shows you how they align the different segments. Because if you don't do that, you won't get sharp images. And look at that, minute movements, about 1/10,000th the diameter of a human hair. That's each step that the motor can move the mirror. Again, amazing piece of engineering. So you point at a bright star, and because this is not aligned, you have, images everywhere. But if you align the telescope, the mirror properly, then you'll have one image. And when that is done, so you have a computer algorithm which can compute how much you have to move each of these segments. And that's how they align it, and they check it every few days. Quickly about the Webb's orbit. Where is it? It's not going around the Earth, okay? It is actually, if you look at the solar system, you have the sun and you have the Earth, which is about 150 million kilometers away. The James Webb Telescope is orbiting a point which is about 1.5 million kilometers away from the Earth, okay? The moon is about 380,000 kilometers away. Is orbiting around a point called the L2 point, and I'll talk to you quickly about that. But that's where it is. And what happens is that it's at this point that as the Earth goes around the sun, the James Webb Telescope is always following the Earth. So it's always behind the Earth and is protected from the sun. So what are these Lagrangian points? These are actually points where the gravitational forces of the two bodies, the sun and the Earth, they actually balance the orbital motion of the satellite. So you put any object at these points, their gravitation is stable. Now, if you move it from this point a bit towards here, it'll be pulled by the sun. If you move a bit towards here, it'll be pulled by the earth. But right over here or right over here, on these points, its gravitation is stable. It's only pulled in. So we located at L2 because we want the telescope to be behind the earth, protected from the sun. And actually, it's not exactly at the L2 point, it's actually having a small orbit orbiting the L2 point, but is moving along with the Earth around the sun. So as you see, you cannot do a rescue mission. If something goes wrong, we lose the telescope. Again, how do we get the data? If you see, it's not like what we have on the Earth, and we are used to this high-speed data. You're getting at least a day, we get about 57 gigabytes of recorded data each day. That's how we can download them. Maximum data rate is 28 megabits per second, which is a lot more than what we are using right now for this internet talk. And it takes about 5 seconds for data to travel from the web in its orbit around L2 to the Earth. 5 seconds to reach us. NASA uses 3 observatories around the Earth to actually always be in touch with the James Webb Telescope. So that's the telescope, and I want to talk to you quickly, given the amount of time I have, about some of the observations, because it has blown us away. We have to figure out now new theories on how some galaxies form, how black holes form. But let's start with the first thing that they saw, which is called the Webb's first deep field. Now look at this image that you see. Imagine taking a grain of sand and holding it at arm's length. That's a part of the sky that the James Webb Telescope saw. That small part. And look at all these objects that they're seeing. Each object that you see is a galaxy. Each of the galaxies has 100 to 200 billion stars. And this is one small part of the sky. You see different forms of galaxies. The galaxies which are towards us and closer to us are brighter. The galaxies which are far away are actually redder because the light from that has stretched. Remember the cosmological redshift? So we are seeing galaxies closer to us, galaxies far away from us. But what you're seeing is actually the picture of what is called a galactic cluster. Okay, it's a cluster of galaxies. Now you see these elongated arcs. These are actually galaxies behind this galactic cluster. This galactic cluster is 4.6 billion light years away. So light left that cluster of galaxies 4.5 billion years ago. But these small stretched objects that you see, they are called gravitationally lensed objects. We see them because the gravity of this cluster between us and the distant galaxies is magnifying that galaxy. Einstein came out with this theory called gravitational lensing. And that's what we see are these arcs, which are actually galaxies about 13 billion light years away, which means that light left it about 13 billion years ago, and we're seeing it now. On the left-hand side was the same picture taken by the Hubble telescope, and it took 11 days to take that picture. On the right is a picture taken by the Webb telescope. It took it less than 1 day, about 20 odd hours. So you see how powerful the James Webb Telescope is. And also in the James Webb Telescope, we are seeing fainter objects, infrared, that we couldn't see in the Hubble Space Telescope. Just to give you an idea how insignificant we are, each of these galaxies, 200 billion stars in the galaxy, and there are 200 billion galaxies. Just to give you an idea, if you ever go to a beach next time, take some grains of sand in your hand and start counting the grains of sand. The number of stars in our universe is more than all the grains of sand in all the beaches in the world. Think about that. Think about how insignificant we are. We are one small star in one small galaxy in a universe. And some of us think There could be multiple universes, for all you know. I'm going to skip it because we are actually going short of time. But here again, some more images of galaxies which are interacting. Because if you go back in time, the universe was smaller and the galaxies actually collided with each other and became larger galaxies. Here's an example, what is called the Stephen's Quintet. There are 5 galaxies, but actually it's these 4 galaxies which are in a cosmic dance, gravitationally bound to each other. The one galaxy to the left is closer to us. But in space, as we see, it looks like 5 very interesting galaxies together. On the left is a picture taken by the Hubble Space Telescope, and the right is a picture taken by the Webb Telescope. As you can see out here, 2 galaxies are actually colliding right now. The galaxy on the left is about 40 million light years away from us. That's closer to us. It's not gravitationally bound to the 4 other galaxies. These 4 other galaxies about 290 million light years away from us, and they're gravitationally bound. The other thing we can do is by studying the spectra. This galaxy on the top, we have been trying to study what is the center of the galaxy. And we know that at the center of every galaxy, we have a huge, massive black hole. Some of the black holes at the center of the galaxies are a billion times the mass of the sun. And a black hole is an object which has collapsed so much that even light cannot escape. So we cannot detect black holes directly, but we can detect the flow and the motion of gases or stars going around the black hole before they are sucked inside the black hole. So here what it's doing, we're studying the different gases, argon, neon, molecular hydrogen. We could only see with a good telescope. And we figure out the speed that it's going around that central object. And the only way you can say a central object which is so massive, it's about as massive as 40 billion suns, and in a very small part in space. The only way to define that is a black hole, a supermassive black hole. So here we have indirect evidence of a huge black hole at the center of one of the galaxies over here. Here's again another picture of a picture of two colliding galaxies clusters. So galaxies also come in clusters, and here's a picture of 2 clusters coming together. And here's a picture on the left by the Hubble Space Telescope, on the right by the James Webb Telescope. Again, you see this gravitational lensing of galaxies beyond the cluster. The cluster is about 4.3 billion light years away from us. The 2 clusters are actually colliding. But what is interesting is that we looked at one of the gravitational lensing galaxy, which is about 3 billion. It existed about 3 billion years after the formation of the Big Bang. So it's far beyond the galaxy cluster. But in that gravitation lens, we saw this object which is actually varying in brightness, but it's very massive. It has magnified about 400 times, and it's called Mothra. It's a star that is magnified by a factor of at least 4,000. So they are studying a number of these transients in this gravitationally lensed structures. We are learning more different kinds of objects in the universe than before. So this Mothra is not really magnified with the gravity of the galaxy cluster between Mothra and us. There's also what is called mini-lensing. The globular clusters actually acts as the mini-lens. So it's very complicated, but it's very fascinating. So going from galaxies, let's go to star-forming regions. So here's something called the Carina Nebula. And here's a picture taken from the Earth. It's actually a place where stars are forming. It's about 7,300 light years from the Earth. It's a huge bubble of gas. But this is what the Hubble saw, years ago. This is the edge of a cavity inside that bubble. But look what happens when the James Webb Telescope looked at it. So now you're seeing the image by the Hubble, and then you'll see slowly the image taken by the James Webb Telescope. You see the difference now? We see so many things going on in the James Webb Telescope. Look at the difference. So that is what the James Webb Telescope saw. That's what the Hubble saw. That's what the James Webb Telescope saw. But then we see so many things going on. This is actually, as I said, the edge of a bubble. The bubble has been, the cavity has been created by very hot stars above this edge of the cavity. The hot stars, the radiation of the hot stars are eroding away the gases in the bubble, so causing the gravity, but just to give you an idea of how huge, you see these pillars out here? These are about 7 light years across. Light would take 7 years to go from one end of the pillar to the other end. These are huge pillars. It looks like a small picture, but imagine how big it is. To give you an idea, at the speed of light, you can go around the Earth 7 times in 1 second. At that speed, you can go to the moon in about 2 seconds. You can go to the sun in 8 minutes. Okay? But at that speed, it takes you 7 years to go from one end of this cliff, or we call a pillar, to the other end. These are huge objects. Also, we'll go back a second. You see these wisps out here. These are actually hot ionized gases as a result of the radiation from the young stars, and also hot dust. We can see kind of eroding away from the pillars. It's amazing what we can see. Other thing is, what you have seen in our solar system is a moon of Saturn called Enceladus. This moon is very, very interesting because we think there's an ocean of water below that. And we know it's true because through the cracks on the ice on the surface, we see geysers, as you see on this image by the Hubble Space Telescope. But look what the James Webb Telescope saw. Again, it's looking at an infrared image of this plume, but the plume is huge. The plume is actually 20 times the size of the moon itself. So here's the moon is right over here, Enceladus, and here's a jet, but the jet of the geyser is actually, and the geyser is made up of ice and water, and is actually 20 times the size of the moon itself. Again, without the James Webb Telescope, you wouldn't have seen that the plume was so huge. With the visible telescope, it's very small. So this is an interesting object. We also have seen the most distant black hole. As I said, this black hole was formed about 470 million years. But this black hole is about 9 million times more massive than the sun. And we think this black hole resides in a galaxy whose mass is about the same mass as that of the black hole itself, a little more. And that's an oddity, because if you look at black holes on other galaxies, the galaxy's mass is about 60 or 70 times more than the mass of the black hole at the center of the galaxy. But in this case, you're looking at a black hole on the earliest black hole we've ever seen, and the mass of the black hole is almost similar to the mass of the galaxy. Again, what we think how black holes are formed does not answer this question. What you're seeing out here actually X-ray emission from the black hole as seen by the Chandra Observatory, the pink area, while the actual black hole is at the center, and we can see it by the James Webb Telescope. So we know that black holes can form from stars which collapse and from a black hole, and then all the small black holes can come together to form a big black hole at the center of galaxies. But how come you have a galaxy which is so young and yet have such a massive black hole? We don't understand that at all. Black holes cannot form that quickly. So there has to be a new way that black holes form. Maybe they form from a huge, massive cloud of gas, and they all collapsed from a black hole. We don't know. As I said, we have to go back to our drawing boards. All you physicists have to go back and figure out how we get from a black hole that early in the formation of the universe, when we think black holes take time to form. Here's the Horsehead Nebula. It's actually a nebula in a galaxy. Again, it's very interesting. On the left is taken by an instrument called USLID. It's visible and the infrared. On the middle is the Hubble telescope that took it with the infrared cameras. And on the right is the Webb. And you can see it closer in close range. Why is it interesting? What we see, the blue part that we see is cold molecular hydrogen. On the top part, the reddish part is atomic hydrogen gas. This is the top of that pillar. It's actually a pillar of gas where stars could form, or planets could form. And the width out here is about 0.8 of a light year. So you're looking at a very small part of the Horsehead Nebula. And you can see this glow over here. This glow is made of dusty silicates and soot-like molecules on the Horsehead Nebula, which is causing it to glow. And that can be seen by the James Webb Telescope. You can also see distant galaxies in the back. Finally, I'm going to talk about the Eagle Nebula, because you have seen this picture before. It's called the Pillars of Creation. It's again a nebula in our galaxy, about 6,500 light years away from us. What you're seeing is a small part of that taken by the Hubble telescope. And these are pillars of gas. It's a part, right over here, you have hot stars, which are eroding away the less dense gas, and which are actually keeping the most densest gases together to form pillars. But that's the taken by the Hubble Space Telescope. And here's a picture taken of the top part of the pillar by the Hubble Space Telescope. The reason I'm showing you this part is if you look at the small finger-like objects on the top, these are the size of a solar system. These pillars out, as I said, is about 5 light years across. And the tip of all these finger-like objects is the size of a solar system. And at the tip, a new star is forming. And the star is actually shielding, is like a shadow, shielding the rest of the pillar from the radiation. That's why we have these finger-like objects. So we're seeing new stars forming. And this is from the Hubble Space Telescope. But this is what the James Webb Telescope saw. Again, we see more in detail. But you see this red spots out here? These are actually jets emitted by newborn stars. You can only see in the infrared. We don't see it with the Hubble Space Telescope, but we do see it with the James Webb Telescope. You're learning more about star formation in these objects through these infrared telescopes. Again, you know what? I'm going to, Dr. Venkatagiri, I'm running out of time, right?
No, Dr. Jaydeep. We would request you to continue, please.
Okay, I want to talk to you about these three because these are the big mysteries of the early universe. So the first one is the number of bright galaxies in the early universe. So if you look at this picture of the Hubble Deep Field, if you look at a galaxy, one of the reasons it's very bright could be because it's closer to us. So if it is bluer in color, it's closer to us. If it's reddish in color, it's far away because the light has been stretched. But a galaxy, the more mass it has, the more stars it has, the more brighter it'll be. So we can look at this picture, count the number of bright galaxies, and figure out how many bright galaxies are there at a certain distance away from us. The James Webb Telescope actually saw a number of bright galaxies, again in the infrared, so it doesn't appear to be very bright, but they're actually very bright in the infrared. But in the early part of the universe, we do not expect such big galaxies in the early part of the universe because the galaxies are not grown as yet. Some of them come together to form groups of galaxies. But why do we have these very bright galaxies so far away from us, which means at the beginning of time? Again, here's the Hubble's ultra deep field, and here's the JW image, and all these objects that you see, these are actually bright galaxies in the infrared because they have been stretched. So, possible explanations, we are seeing them to be bright because they're due to the first stars that were formed that are brighter and bluer than the modern stars, but we have yet to see those stars. We are seeing a result of the stars forming as a bright object, but we don't see the stars itself. This is a possible hypothesis why we are seeing so many bright galaxies in the early parts of the beginning of the universe. That's one. So here you go. As you see, most of the reason this star is very bright is because a lot of stars in this galaxy which makes it appear very bright. Here's an artist's conception of what the universe might look like when the first stars form. We haven't seen it as yet. Okay? But we think the one way to explain why we have so many bright galaxies in the early universe is because we haven't spotted the first bright stars. That's one. Other one, there are going to be starbursts. And there could be a number of such starbursts, which are brief star-forming episodes. So we're seeing a number of stars forming quickly, and that's why it dramatically enhances the galaxy's brightness. So here's an artist's conception of early starbursting. Again, we don't see those episodes of starburst. We're just guessing that this could be a reason why we are seeing so many bright galaxies in the infrared. So you don't see it with the visible light, so it doesn't look bright to you. But the infrared is very, very bright, and this could be one reason. Again, we don't have any answers. So that's one unanswered question. Second one is amount of heavy elements in the early universe. So hydrogen and helium, they are the main parts. Most of the universe is made up of hydrogen and helium. The other heavy elements form later on in stars. So what we expected and what JWST is finding. So we expected the early universe to be composed mostly of hydrogen and helium. Makes sense. The early universe was made up mostly of hydrogen and helium. Stars are not formed as yet, or maybe just forming, and the heavier elements are formed inside stars. That's what we thought. We'll see hydrogen and helium. But we have detected carbon, oxygen, neon, and even hence in galaxies, which were only formed hundreds of millions of years after the Big Bang. So here's an example of one of the most distant galaxies we have observed. It's called Jades, and they gave it a number. But it was formed 290 million years after the Big Bang. That's amazing. That's the farthest we have seen any galaxy. And that's the infrared image by James Webb Telescope. But here's the interesting part. When we look at the spectra of the galaxy, we look at the light, and from that light we can figure out what are the elements that are blocking certain parts of the light. We see oxygen. This was taken by millimeter telescope on the Earth, which can detect in the large millimeter and sub-millimeter part of the electromagnetic radiation. Two independent studies have shown from this Atacama Large Millimeter Array in South America, they have shown oxygen emission lines. We shouldn't see that in an early galaxy. We shouldn't see any heavy elements at all, or maybe very small traces of it. And oxygen is, way beyond hydrogen and helium. Again, we have seen a number of young galaxies, and we have seen on the spectra, we are seeing all these heavy elements which should not have formed if we understand how galaxies form and how stars form. So what are the implications of this mystery? We know metals are formed in stars. When you see metals, I mean, apart from hydrogen and helium, the heavy elements are formed through nuclear fusion inside stars. And when the stars explode, they disperse it into space. That's how we were formed, by the way, right? We are basically carbon-based life form. Where did this carbon come from? This carbon came from other stars which exploded, which formed carbon, exploded. This carbon then was dispersed in a galaxy, and then when our solar system formed, we had the carbon to form life. So all these heavier elements are formed inside stars. And of course, if you see more elements, it means the stars have gone through a number of generations. Each star, depends on the mass of the star, could live anywhere from 1 billion to 10 billion years. But if you're talking about a lot of heavy elements, we expect multiple generations of stars to have lived and died. And that's not the case with early galaxies. It's only 290 million years after the Big Bang. So how do you have all these heavy elements if the stars take so much time to form? So early galaxies are surprisingly rich in these heavy elements, which means that the first stars that were formed were more efficient in creating and spreading these elements than what we know right now. It's a mystery. We have to figure this out. And finally, this is something new that has come out. It's called the little red dots. Okay? So what is it? The little red dots were discovered when they were doing a survey of supermassive black holes in the distant universe, 100, 200, 300 million years after the Big Bang. So you see them, these are in the infrared. That's why they'll appear red in color. And they're called the little red dots. They all exhibit similar features, but they're only seen early in cosmic history, not now, earlier on. All of them are very massive, but some are compact, some are actually extended, and some of them show evidence of a black hole at the center, while others do not. So it's a variety of morphology. So again, these are compact, elongated, extremely red objects at high redshift. High redshift is just another way of saying they're far away from us and formed a few million years after the Big Bang. So here we're talking about 480 million years to 1.7 billion years. They were found in these deep fields doing the survey, and they appear more massive and numerous than expected this early in the cosmic history. So initial explanations, again, hypothesis, they are early massive galaxies. There's rapid star formation in these galaxies. The problem is it's too fast and it's too early for stars to form. So are there early massive galaxies? We don't know. It could be that there are starbursts in these objects. This is because there's a lot of dust in these objects. They're red in the light, and we see it as red. But as we know, there are not enough metals in this early universe for dust to be created. Is it possible that we're seeing it edge on as a disk, but we don't see these bars in galaxies this early in cosmic history? And it could be that we do not have the distance right, but we have confirmed it through spectroscopy that they're very far away from us. So these interpretations strain standard cosmology timelines. It's actually making us go back to a drawing board. One very radical explanation, this is very recent, is that they are what we call black hole stars. So these are massive objects, about 10 to the 4 to the 10 to the 6 times mass of the sun, which is a black hole inside that stellar envelope. So imagine like a star, on the inside of the star is a black hole. Not exactly that, but this is what they think it is. And they think that the radiation from the accretion of gases around the black hole causes the outer layers to shine brightly in the infrared. And they form rapidly from dense primordial gas. This is just a hypothesis. We have no evidence for it. And what's the relevance to red dots? It could mimic galaxies, these black hole stars. It could mimic galaxies in brightness and color. And it could be a seed for other black holes, supermassive black holes in the past. But problems. Again, as I said, if the massive galaxies, the timeline is too short for such large systems to exist. If the dusty starburst galaxies, dust takes times to build up, and we didn't have time for the dust to build up. Talking about seeing them edge on, but these bars are not seen so early in galaxies. So if the little red dots are truly massive galaxies at large distance, they suggest galaxy formation was faster, earlier, and more efficient than standard cosmology allows, which implies new astrophysical formation channels would figure out new ways how these form, or we modify a cosmological model. And finally, we think, I talked about the most distant galaxy was 290 million years after the Big Bang. So we have James Webb Telescope has seen this object. We don't know exactly what it is. But if we, through photometry, not through spectroscopy, through photometry, we think it was formed about 90 million years after the formation of the universe. And that's a problem. If it is a galaxy, how does it form? So they have been associated with, it's called Capoturo. It's an Italian name. We don't know exactly what it is. If it could be that this object is in our galaxy because we don't know the distance through spectroscopy. So if it is within a galaxy, it could be an exoplanet which is flung away by its host star, or it could be a brown dwarf. A brown dwarf is a star which did not form. Maybe 10, 20 times the mass of Jupiter, but did not form a star. If it is outside a galaxy, it has to be very far away for it to give us that reddish color. So it could be a hypothetical black hole star, or it could be close to us and very dusty. So if it is outside a galaxy, it's either closer to us, but it's very dusty, or it's a black hole star far away from us. Again, we don't know the distance very well. But one of the theories is that, it's not theory, hypothesis, I would say, it's a galaxy observed at a time when the universe was 90 million years old. The object's apparent luminosity that appears to us because we don't know its actual luminosity, because we don't know its distance very well. It's about 1 billion times of the sun. And to achieve such a mass, the efficiency of the galaxy turning gas into stars has to be 100%. But that's not the case what we see in galaxies so far. It's about 10 to 20%. That's how we can transform the gases in a galaxy to stars. But to explain this one, if it is a galaxy, there has to be a way of taking all the gas in the galaxy and forming it into stars. 100% efficient. We don't know. So I'm going to stop here and just show you, this is what James Webb is observing about an hour ago, is observing a supernova in some other galaxy. Stars and stellar populations is using these two instruments to look at it. Now, anyone can actually submit a proposal to the James Webb Telescope organizers, and if your proposals succeed, then they give you time on the James Webb Telescope. Here's someone whose proposal was, of course, accepted, and now the James Webb Telescope is pointing towards an object, giving the data. And the way it works is that these PIs, the people who are doing the observing, they have 1 year to work on the data and get results out. After that, is given out to the public. So anyone can go and download the data from the James Webb Telescope, anyone, and work on it. I'm going to stop over here. I know I took a lot of your time, but thank you for all the students who have taken the time to listen to this presentation, because I think it's amazing. I learn every time I give a talk, venturically. I try to show something new because we're learning something new. I don't know if you have any time for questions, but if you don't, I can always answer questions via email.
Thank you so much, Dr. Jaydeep. That's a breathtaking presentation, as breathtaking as the telescope itself is. Dr. Viswanathan, sir, would you like to make a comment on Jaydeep sir's presentation.
No, it's a wonderful lecture we had, presentation. We came to know a lot of informations, and really on behalf of your organization and our university from India, we are thankful to Dr. Jaydeep Mukherjee, sir. Thank you very much, sir. Extremely very good lecture we had.
Welcome.
Dr. Jaydeep, there is only one question. I mean, among all the discoveries of the JWST, which one do you think has been the most rattling one, which has something like questioning our understanding of our universe so far? Which has been the most rattling discovery so far?
The three that I've shown. I
Okay.
talked about the early bright galaxies. We talked
Okay.
about the black holes, early
Yep.
black holes, and the little red dots. We don't know what
Okay.
they are. So
Okay.
all these things are going to make us figure out how black holes formed.
Okay.
What of the Big Bang? So we think there are a lot of hypotheses about the universe, right? So maybe the universe is infinite, and we are a part of an infinite universe, the observable universe. So observable universe is about 80, it's about 40 billion light years across. The age of the galaxy is only of the universe is 13.6. But when the Big Bang took place, the Big Bang, by the way, is not an explosion. It was a name given in jest by some opposing. It's not an explosion, but it's the formation of a universe. But at the beginning, 10 to the minus 21th of a second, we had what is called an inflationary space. The universe expanded rapidly within 1/20,000th of a second. So rapidly that what we only see is about 40 billion light years across. But only objects that left 13.6 billion light years ago, because that's the age of a universe, 13.6 light years. Anything beyond that we cannot see because it's beyond our observable universe. Now, there are hypotheses that there are multiverses, and the reason they think there are multiverses is because we have this what is called dark energy, which is actually making the universe actually expand faster and faster. We saw that started about 5 billion years ago. The only way to explain that is some repulsive force we call dark energy. To explain dark energy, we sometimes have to evoke multi-dimensions, 10 dimensions, 12 dimensions. We have something called string theory to explain all these things. And again, to explain this dark energy and string theory and 12 dimensions, it leads to multiverses, different universes. No evidence for it. But this is what's the interesting part, right? You can guess, you can hypothesize. It may not be true, but you can hypothesize, and that's what makes things very, very interesting. And we'll learn more. We'll learn more about
That is true.
the universe with the change. Maybe in my next talk, maybe in 3-4 months.
Yes.
And there were so many more things that I couldn't show because of lack of time.
Please.
But
That will be an
next time we'll
opportunity.
check.
That's a great opportunity for us. Thank you so much, Dr. Viswanathan, sir. Thank you so much, Dr. T.P. Das. You have made this a great success. And Dr. Jaydeep's email ID is available. And Dr. Jaydeep will be more than happy to answer questions by email. And we encourage questions by email. Thank you so much, Dr. Jaydeep. Your presentation, as usual, has been breathtaking. And it's one more page of inspiring program that we have done. Thank you again, Jaydeep. Thank you, Dr. Viswanathan, sir.
Thank you, sir. Thank you.
Bye.
Thank you. Bye-bye.
Bye-bye.